So hello and welcome to my presentation on Snowcap, synthesizing network-wide configuration updates. My name is Thibaut Schneider and this work was done in collaboration with Rüdiger Birkner and Laurent Vanwever from the Network Systems Group at ETH Zurich. As network operators, we configure our networks from scratch only once. Changes after that are reconfigurations, and these happen very often. Business relationships between neighboring networks change on a daily basis, which require us to change the routing policies. These reconfigurations only modify a single router, but they can happen up to 20 times per day on average. Networks may face new requirements every couple of weeks, which poses new challenges for traffic engineering. Such reconfigurations involve multiple routers in the network. Now finally, we sometimes completely redesign our networking infrastructure to adapt it to new network paradigms. For this, we must change the configuration of every single router in the network. These medium to large-scale reconfigurations can be extremely disruptive. A study from Alibaba has revealed that more than half of their network incidents are due to changing the configuration. So let's look at a simple example to highlight these issues. Here we have a small network with one firewall and one external peer. Our goal is that the traffic from Rx to the external peer will always traverse the firewall. We can achieve our objective by choosing the forwarding state something like this. And this forwarding state can be implemented using OSPF and these set of link weights. Now let's pick this as our initial configuration. But observe that the link between R2 and the external peer is a single point of failure. And we now want to fix this by adding redundancy. So we add an additional physical link and a BGP peering session between R1 and the external peer. But if we would simply do that, then Rx would bypass the firewall, because it can now reach R1 with a cost of 10 instead of R2 with a cost of 18. Therefore, we also increase two link weights, such that the path from Rx to the external peer is not affected. Let's pick this as our final configuration, and to migrate, we need to make 3 changes on 3 different routers over 2 different protocols. So let's just start reconfiguring the network. What can go wrong? If we first add the session, then, as we already discussed, Rx will bypass the firewall, which is not good. So we first need to increase the link weight between Rx and R1. But if we do that and then add the external session, then we will have an unnecessary traffic shift at the firewall. So in this case, the best way to perform this migration is to first change both link weights and then add the external session. And this can be very easy to see for this small example, but what if the migration becomes bigger? So for bigger migrations, operators typically perform them during low network utilization. This reduces the impact of anomalies. In addition, they try to follow best practices presented in the literature. One of these examples is this book on network mergers and migrations for Junos. This certainly reduces the number of outages and anomalies, but it is not enough, as we have already seen in the case of Alibaba. So we conducted experiments ourselves to see how much these best practices actually help. To do this, we simulate the scenario of moving from an IBGP full mesh to a route reflector topology. And this is a very common migration scenario that most smaller networks will go through when growing in size and complexity. We use around 80 different topologies from Topology Zoo, and we prepare a migration scenario for each of them. Then we pick many different random orderings of routers and count how often some flows end up in a black hole or in a forwarding loop. Now, as a baseline, we select a completely random order of routers to reconfigure. And in 70% of migration scenarios, more than half of these random orderings break reachability. Now, according to the literature, best practice is to reconfigure the route reflectors before all others. So following this best practice yields a slight improvement, but nevertheless, in a quarter of the scenarios, we have a large chance to break reachability. As we have seen, these best practices cannot give us any safety guarantees. But in addition to that, these practices are prepared for a specific protocol and migration scenario, so they cannot be applied universally. This is clearly an important problem, and we're not the first ones to look at it. Existing systems can be distinguished into 2 different categories. Offline systems run the initial and the final configuration at the same time. Then, they wait until the final one has converged, while still forwarding packets according to the old configuration. Finally, these systems activate the new configuration on one router after the other in an ordering that preserves the objective. While offline systems can guarantee safety for any protocols and migration scenarios, They introduce additional memory overhead as the control plane is essentially duplicated, which makes them less practical. On the other hand, online systems directly change the configuration of the live network. They synthesize multiple small changes to the configuration that can be applied to the network one by one. While not adding additional overhead, they only support a limited set of scenarios and protocols, mainly link state IGP. This makes them less practical, as most of today's networks are running a combination of BGP and IGP. So, we present Snowcap, a system that automatically and safely performs reconfigurations on the live network, but is general with respect to protocols and reconfiguration scenarios. Here you can see a high-level overview of the system. As an input, it takes both the initial and the final configuration, which are both assumed to be verified and correct. Then it computes the difference between those two configurations to get a set of commands. These commands are necessary to perform the migration. Next, the operator specifies a set of specifications, which are properties that must be satisfied during the migration. We call those the hard specification. As in the example from before, the hard specification would be that Rx must always traverse the firewall to reach the external peer. The specification language of Snowcap is extremely flexible. It is built by combining a set of basic policies that are reachability, isolation, redundancy, and waypointing, which is a regular expression that matches on a path of a flow. But typically, operators change their configuration to adapt their network to a new specification, so the specification is changing over time and not constant. Therefore, these policies can not only be combined with Boolean logic, but also with linear temporal logic, which adds a time dimension to the specification language. Operators can now precisely express how the migration should happen. Here are a few examples of using linear temporal logic. Let's say we want to migrate a firewall from an old one, R1, to a new firewall, R2. We can express this using linear temporal logic by requiring that all flows must start at the old firewall and then switch over once to the new firewall. We can relax this example a bit by allowing the flows to bypass the firewall for a short amount of time while switching from the old to the new firewall. But we can also restrict this example more by requiring that all flows must switch to the new firewall at the exact same moment in time. So these examples highlight how powerful linear temporal logic is in expressing the precise intent of the operator. In addition, operators can specify a soft specification, which is a cost function that compares different migration sequences. Because not all orderings that satisfy the specification are equally good. For example, we might want to reduce the number of traffic shifts, because these might have a negative impact on the performance of the network. So let's go back to our initial example, and let's assume that we have already increased the link weight from Rx to R1. Now, if we add the BGP session, then both the firewall and R1 will change their next hop, and therefore we will assign to this ordering a cost of 2. And then finally, we increase the link weight from the firewall to R1, which causes the firewall to go back to R2. And therefore, this ordering has a cost of 3. Now, alternatively, we could increase the link weight first before adding the session. And if we do that, if we increase the link weight, then nothing changes in the forwarding state. So this ordering will have cost of 0. And then finally, we add the session from R1 to the external peer, which causes R1 to change its next hop. And therefore, this ordering has a cost of 1. So notice that the final state in both orderings is the same, but one of them has caused more side effects, and therefore we should prefer the other one. Snowcap is not limited to only counting traffic shifts, but it can also be used to minimize other metrics, such as memory usage or even something combined. Based on the initial and final configuration, the hard specification and the cost function, Snowcap will find an ordering of these commands that will satisfy the hard specification while minimizing the cost function. Snowcap will then apply these commands one by one to the network, letting the network converge in between. This way, Snowcap can safely perform the network migration. The main challenge of Snowcap is how to effectively navigate this large search space. Because of course we have a factorial growth of the number of possible command orderings with increasing number of commands. But what makes it even worse is that most of these command orderings are actually invalid. Simply picking a random ordering until we have found a valid one by chance doesn't scale. So how does Snowcap do it? In the following, I want to explain how Snowcap effectively navigates this large search space. In the first part, I explain how the basic exploration mechanism of Snowcap works, and then I will show you how we can extend this mechanism to effectively isolate problems. The main algorithm is based on a depth-first search traversal. So let's look at the example from the beginning. You can see the example on the right, and on the left you can see the current state of Snowcap. At each step in the exploration, Snowcap tries all the remaining commands and picks the one which has the lowest cost. This obviously will result in a greedy optimization and will not necessarily find the global minimum. But still, in the end of this presentation, I will show you that this approximation is really good. If we now execute command A, which is adding the external session, then, as we already know, the firewall is bypassed. So Snowcap will not explore any of the sequences that start with command A, as it already knows that they are invalid. Instead, Snowcap tries the other commands. So applying command C will not change anything in the forwarding state, and neither does command C. So both of these commands have cost of 0, and Snowcap will pick one at random. Let's say it goes with command B. Now again, it tries all the remaining commands. Applying A in this state, so adding the external session, will cause one traffic shift at the firewall. But on the other hand, changing the second link weight does not change anything in forwarding state. So in this case, Snowcap will go with command C as it has a lower cost. And finally, Snowcap will add the external session, which will result in a valid sequence. And actually we have found the optimal solution to this scenario. So this works extremely well in most cases. But what if we get stuck? It is possible that none of the remaining commands can be applied anymore. And this is usually due to a problem earlier in the sequence. Now let's take the example here on the left. And let's assume that command R must be applied after both V and W. Now the DFS algorithm would simply backtrack and explore all the possible options until finally resolving the issue. However, if the problem is earlier in the sequence, this backtracking can take a very long time. Instead, Snowcap actively finds these dependencies. On the higher level, Snowcap is using a counter-example guided search strategy. In the exploration phase, if it gets stuck, it takes one of these failing sequences as a counterexample. Then it tries to isolate the dependency inside of this counterexample. In a divide and conquer manner, Snowcap tries to solve the isolated dependency to find a valid ordering for just this reduced problem. Snowcap then switches back to the DFS exploration, but the learned dependency will now be treated as a constraint that it must appear in this order as we have learned it. With this, Snowcap can solve difficult dependencies in isolation and thus speed up the search significantly. And let's look at how Snowcap can isolate these dependencies. So let me introduce you to a new example. It consists of 6 routers, and the 2 egress routers, B1 and B2, are connected to the same external network. The topology is running OSPF, with link weights all set to the same value, but the BGP configuration is a bit more complicated. We start with these sessions shown here in violet. The lines that are thicker represent BGP sessions that are actually used to learn the routes. But routes advertised over thin lines are not selected. So initially, both R1, R2 and T2 select B2 as their egress point, while T1 selects B1. Now this is the resulting forwarding state, and it is a valid configuration. There is no forwarding loop. Now for the final configuration, we remove the 2 sessions, the 2 direct sessions between B2 and T2, and the one between B1 and T1. In addition, we replace the session between B2 and R1 with a new session between B1 and R2. And this is the resulting forwarding state where all routers choose B1 as an egress point. And again, it is a valid configuration, there is no forwarding loop. So let's solve this problem using the DFS algorithm. And let's assume that Snowcap first picks command A followed by command B. And now all routers choose B2 as an egress point. But if we now try to add the session from B1 to R2, then we get a forwarding loop between T1 and T2, because they select each other. And similarly, if we try to remove the session from B2 to R1, then we have a forwarding loop between R1 and R2. So the DFS exploration is stuck, which means that none of the commands that are remaining can be applied. So how does Snowcap now continue? So we start with the ordering that actually caused the problem. In this case, it is ordering A, B, C. We still have the forwarding loop between R1 and R2. In the first step, Snowcap removes all commands that don't participate to the problem. This is done by removing each command one by one. If the problem is solved or has changed, then we know that this command is part of the dependency. But if nothing has changed, we simply ignore it. So, if we remove command A from the ordering, then nothing happens and the forwarding loop still remains. Also, if we remove command B, nothing happens. So, both commands are not part of the dependency and we have isolated the problem. Then, Snowcap tries to find a valid solution to this minimal problem. And here we use the same DFS algorithm as in the exploration phase. In this example here, there obviously exists no valid solution. So Snowcap then tries to extend the problem with yet unconsidered commands. In our example, the only command that was not yet considered is command D. So we try to put this in front of C and notice that this actually results in a valid ordering. So finally, Snowcap returns this ordering as a dependency group. In all future iterations, these commands will be kept together in the correct ordering. So how does Snowcap scale? And how effective is it at minimizing the cost? To evaluate this, we look at around 80 different topologies from Topology Zoo, and these range from around 10 routers to up to 82 routers per network. We used common migration scenarios described in the book Network Mergers and Migrations by Junos. We used the following three scenarios. First, we migrate from an IBGP full mesh to a route reflector topology. Second, we perform a network acquisition. And third, we double all the IGP link weights. In our paper, you can find even more scenarios. For each scenario, we choose random link weights and a random IBGP topology. And as a side note, Snowcap is only executed on a single thread. So let's go back to the case study from the beginning of this presentation. As a quick reminder, we have simulated a migration from an IBGP full mesh to a route reflector topology. And we have shown that even when applying best practices, in about a quarter of the scenarios, there is a large chance that the migration will cause transient black holes or forwarding loops. Now, using Snowcap, every single migration resulted in no transient anomalies at all. It takes Snowcap around 12 seconds to find a solution for the biggest problem, and this problem contains more than 3,000 reconfiguration commands. And on average, it takes Snowcap less than 1/10 of a second to find a solution. So now, let's look at how Snowcap scales with some theoretical examples. In the first scenario, we created a very simple network that forms a chain. Both ends of this chain are connected to the same external network. During the migration, we want to change the next hop of each router to point into the other direction. In this plot, the x-axis shows the number of commands, so the size of the chain, and the y-axis shows the time it takes to solve this problem. The random approach scales really badly, and this is because there exists only one valid solution. Snowcap, on the other hand, is able to solve this problem extremely quickly. Now in the second experiment, we generate a topology that consists of many difficult dependencies. Each of these dependencies is such that a bad decision earlier can lead to the DFS exploration getting stuck. Each of these dependencies contains 3 commands and is independent of each other. The x-axis shows the number of these dependencies and the y-axis again shows the time. Again, the random approach scales really badly. However, the approach with the DFS exploration only scales even worse, and this is because it needs to backtrack really often. But the counterexample guided search of Snowcap really shines in this experiment. So let's now look at how effective Snowcap is at minimizing the cost. Snowcap only performs a greedy optimization, so it is not guaranteed to find the global minimum. In the following, we will look at 2 different scenarios and try to minimize the number of traffic shifts during the migration. In the first experiment, we perform a network acquisition. Here we add several physical links and IBGP sessions between the 2 networks, and we rescale the link weights of one network to fit the other. On the x-axis, we show the different scenarios and topologies, and on the y-axis, we compare the number of traffic shifts. This red line is the number of traffic shifts when performing the migration in a random order without actively minimizing the cost. In comparison, Snowcap typically is able to reduce the number of traffic shifts by about half. Unfortunately, we cannot show the theoretical minimum as we don't have hundreds of years of compute power. In the second scenario, we do the same thing but for doubling all the link weights. Here, Snowcap performs even better, usually finding an ordering without any traffic shifts, while the random strategy does not. Finally, let's look at the overhead that we have to pay in order to do the greedy minimization. For this, we perform the scenario of migrating from an IBGP full mesh to a right reflector topology. On the x-axis, we show the different topologies from topology zoo, and on the y-axis, we show the number of states explored in a logarithmic scale. So here we can see how many states Snowcap explores when only considering the hard specification and without minimizing the cost function. But when we greedily minimize for cost function, Snowcap roughly explores the square number of states. And this is because at every step in the exploration, Snowcap must consider all the remaining commands. And now for comparison, here's the number of states that we have to explore when randomly picking orderings until the first valid ordering was found. Now we can see that there clearly exists a cost that we have to pay for the optimization, but it is bounded and doesn't explore. And still, we are sometimes much quicker than the random approach while also giving us better results. So to recap, Snowcap is a system that is able to safely and automatically perform network-wide configuration updates. It does work for arbitrary protocols and arbitrary scenarios, and it doesn't pose any additional overhead to the networking infrastructure. If there exists a valid solution, Snowcap will find it. Snowcap is open source, and you can find the source code and the documentation on the project website. So this concludes my presentation. If you have any questions, I will be happy to tell you more about the system. But otherwise, you can find all the important information in our paper or on our project website.